everyone, and welcome to a new Students' Final Project presentation ceremony from our Masterclass students. For today, we have two very interesting and very different presentations. The first one, which is going to start right now, is by Angelo, Amador, and he's going to be presenting his ROS2-based humanoid robot. And then after the first presentation, we're going to have the second one by Alan, and he's going to be presenting to us his autonomous shelf finding and delivery robot based on a warehouse environment. So yeah, I hope that you enjoy both presentations, that you can learn something from them. And as always, remember that after each presentation, we are going to have some minutes of questions and answers. So if you have any specific questions that you would like to ask to the students related to their projects, please share them here in the YouTube chat. I'm going to be reading them. And if I see any interesting question, I'm going to for sure share it with the student for him to answer it and to clarify any doubts or questions that you might have. So yeah, welcome everyone, and let's not lose any more time. Let's already get started, and let's say hello to our first student, who is Angelo. We are seeing you already, Angelo. So yeah, the audience is yours.
Okay. Hello everyone. I'm Angelo from Mexico, and I want to present you my project, which is a ROS2-based teleoperated humanoid robot. So first of all, I'm going to share my screen. Please let me know if you can see.
Yes, we can see it. We have it.
Okay, so here we have the robot. So let's start with the demonstration. Here, as you can see, I can control the robot from the terminal, and I can make different movements with the in the terminal to move in order to move the arms of the robot. I can move the right arm or the left arm or both of them at the same time. So here, as you can see, we have different movements. I also can rotate the hand of the robot. Here, as you can see.
So this is live, right, Angelo? You are controlling
Yeah,
it right now.
this is live.
And that robot is in Mexico, I think, correct?
Yeah, it's in Mexico.
Okay.
So this robot is not with me, and I also can visualize the web page of the robot. This web page allows to visualize the camera, and this in the camera is able to we can see different objects that are detected for the camera, and in the right part of the web page we have a list of the objects detected. Here we have the last 5 detections. Okay, so overall this is the project. So I hope you enjoy this project. But this project was made for myself from scratch. So let's deep into it. Okay. So what does it consist of? Okay, this project includes different technologies and also different skills. Of course, we have the ROS2, Ubuntu, Docker, Arduino, Python, but also for the CAD modeling, I use Fusion and a 3D printer. And of course, we have the microcontrollers and the central computing, which is a Raspberry Pi. Okay, now we have the current capabilities of this project, which is a real-time upper body teleoperation, a multi-joint actuation through ROS2 topics, a remote keyboard control interface, a distributed micro-ROS embedded control, and head and upper limbs interactive motion. Okay, so the first part is the mechanical design and additive manufacturing. So in this part was the CAD modeling in the Fusion software. And the design includes the head model, arm models and the torso frame. And this was thought to be friendly assembling and to has a very good modularity. Here we have the joint kinematics considerations, and the range of motion of each servo was limited mechanically to avoid collisions, and also have some joint kinematics considerations, which are the movements of the head and the arm. And here we have a video of how the process of the printing works. Here, in this case, is the printing of one hand of the robot. Okay, and then continue with the technical specifications. First, we have the actuation system. This system consists of the servo motors. Here we have a smaller one. This was planned to be to work for the fingers. So this need to be lightweight and also compact. So in that case, it can be easily mounted in the robot. And also its purpose is the finger flexion and extension. Now for the wrist, we have a higher torque servo, which is a MG996. And for this joint, we need more torque. So this also means that this servo is bigger. And then for the elbow joints, I also use high torque servos, but in this case it's 40 kilograms because it needs to support larger mechanical loads. Then for the upper arm joint, we also have a MG996 servo because it doesn't need that much torque. So that's why I use this. And for the head mechanism, which is composed by 2 degrees of freedom, we have these two servos for the movements from right to left and up and down. Okay, now we have the power system. And in this case, I use a LiPo 2S battery because this can deliver a high peak current, and it also brings a suitable voltage for mixed servo types. And it's also stable under multi-servo load. Okay, then let's continue with electronics and control. For the electronic components, the most important ones are the power distribution bus and the voltage regulator, because the servos will be working in a different voltage than the one that supplies the LiPo 2S battery. So I need to regulate the voltage. And of course, we have the microcontrollers. In this case, I use a ESP32 boards, which were used for the sensor transmission, micro-ROS servo control, and wireless communication. And the central computing, which is a Raspberry Pi, used for ROS2 middleware, topic management, and teleoperation coordination. Okay, so here we start with the ROS2 software architecture. This is the overall system architecture. First, we have the user input, which is with the keyboard commands. And then we continue with the ROS2 teleoperation nodes. Then we have the ROS2 topics. And from the ROS2 topics, we continue to the micro-ROS agent. This micro-ROS agent will be working in the Raspberry Pi. And then we have the subscribers that will be working in the microcontrollers. So in this case, they will receive the data and make the PWM to make the servo control and then the robot motion. Okay, this is a 4-layer architecture. The layer 1 is the user input, which is the keyboard teleoperation node. Then the second layer is the ROS2 middleware, which includes the ROS2 nodes, the publishers and subscribers, and the topic-based communication. And here we have some topics that are the ones of both arms and the head. Then the layer 3 is the embedded control layer, which is the one that um, has the micro rods. And then we have the last layer for the actuators. Okay, the micro rods integration. This was used because it can uh, we can it can allow the communication between the central computing and the microcontrollers. And each microcontroller will have it's a ROS2 subscriber that will receive commands and generate the PWM and make the servo movement. Okay, and the communication between the microROS agent and the F32 microROS client can be with serial or Wi-Fi communication. And in this project, I had different challenges and engineering trade-offs. One of them was the latency, because, for example, in the camera, we can have some lag. So this is a big challenge. Also, I can have a wireless instability. About the power requirements, it's because the LiPo2S uh, can works properly with this type of servos, which I work with. But if I use more powerful servos, it would be enough. So I also have the servo jitter, the debugging embedded ROS2 system, which is the ones of the micro ROS. But it was also a big challenge because it was a bit difficult to integrate it is in different microcontrollers, but at least I can do it. And also, since my servo motors doesn't have any encoders, that's why I have some limitations with the simulation, and it represents a real hardware constraint. Okay, so here we have the how it works, the remote teleoperation mode. Here we have the Raspberry Pi, and we have three different microcontrollers. Two of them are for the arms, and one of them is for the head. And the ROS2 node will capture key inputs, which are from the keyboard, and it will publish the data, and all the microcontrollers will be the subscribers. So in this case, the communication is serial, just for two microcontrollers, because the Raspberry Pi only has two blue USB ports, and the other one the third microcontroller was just with Wi-Fi communication. And of course, I use ROS2 Humble inside the Raspberry Pi, which works with Ubuntu. Okay, we have some considerations for the remote teleoperation mode. And it is very important to use Docker in this project because for registering my robot to the construct platform, I use Docker. And then in that way, I can use the ROSject to control the robot with SSH. So in that case, I can enter to the terminals and run all the programs to start working. And this is a representation and simulation of the robot. This is ongoing because I faced several challenges. For example, here is we can see the RBs, and I can move the joints in RBs with different values. And the gazebo is is below, in the window below, because it is not finished. Because sometimes when I try to make the simulation work, the arms have some problems and doesn't appear in the gazebo simulation. So that's why this is ongoing. And then we continue with the object detection system using YOLO. And as I mentioned before, this system will generate some images with bounding boxes and labels. So the robot can identify different objects in real time. For example, it can detect a person, a chair, a plant, many objects. And here we have an image of how the camera detects different objects and its names. And then we have a video of how it is working when the head of the robot is moving. Of course, with some lag, but you can see how it updates in real time. And also we have a web interface. This use a HTML, JavaScript, and ROS libs. And the communication between the web page and the ROS2 is achieved through ROS bridge, which provides a WebSocket. So this allows the connection between the browser and the ROS2 ecosystem. And here we have another video of the robot working, moving the arms and the head. Okay, so the results of this project. We have a web page visualization, a real-time control with a keyboard, ROS to S32 communication with micros, wireless communication, object recognition using YOLO, 3D design and printing, and smooth actuation of head and upper lip. And for future work, I'm planning to do the vision-based autonomous manipulation, predefined gestures, stronger materials for the robot, like nylon, and the full dynamic simulation with gazebo and RVs completed, uh, working completely. So to achieve this, it's also important to use servo motors with encoders. So that's everything, and I hope you really enjoy this project. Thank you so much.
Okay. So thank you, Angelo, for the presentation. All right, then. Yeah, let's go with the questions. I have
Yeah,
many. I have many questions myself.
yeah.
So, for the people who was here in watching the presentation, please go ahead and share your questions here, and I will be reading the ones that I consider myself that are more interesting. So, let me start myself. Like, for example,
Mhm.
my very first question is, why did you decide to build a humanoid robot? So what was the reason behind
Mm.
it? Did you have a specific goal in mind to achieve, or?
Yeah. It is because I wanted to design a robot that can be more interactive with humans, with people. So I think humanoid is a very good choice. So that's why I wanted to design a humanoid robot from scratch.
Mhm. Okay, and why did you decide to do only the upper half? So you didn't want to deal with all the walking kinematics and all that, or?
Yeah. Because yeah, because for example, if the robots have some legs, it would be very challenging. So it's also very difficult because it represents that the robot needs the legs of the robot needs to support all the weight of the upper part of the robot. And if it is in motion, it will be very difficult. So it's very challenging. And I also need to add some more components, and it also represents more powerful power system. So it was very challenging, and I also need more time to design that type of robot.
Okay. Sounds fair enough. Fair enough. Okay, so more questions because we saw there at the beginning with the demo in the project.
Yeah.
And you explained a little bit in the presentation, but it was not so clear to me how you manage all the connection to the robot. So could you show us a little bit more of that? How is exactly
Yeah.
established the connection to the robot?
Yeah. Okay. Mm. Okay, here we have and in the first five, I'm connected with the robot with SSH.
Mm-hmm.
So I'm running different programs. For example, the microROS agent is running in the 1 and 2 terminal,
Mm-hmm.
and this microROS agent will be communicating with the microcontrollers,
Mm-hmm.
and the third terminal will be running a Python script, and this script is the one that will detect the user input with
Mm-hmm.
different keys from the keyboard, and it will send the data to the microcontrollers. And then
Okay.
we have the fourth and five terminals are for the click detection. The five will be running the YOLO,
Mm-hmm.
and the fourth one will open the camera. And then for example, the number six will start the web page, and the seventh one, here we have because it's not visualizing properly, the server is the server.
Mm-hmm.
So I can enter to the web page.
Okay. Okay. Yeah.
So mainly this is how it works.
So essentially, you established the connection through the remote lab service in the construct, and then
Yeah,
from there you do an SSH and get inside the robot, right?
yeah, sure.
Okay.
Yeah, it's
Okay.
in that way.
Okay. And now that you
Mhm.
were showing this, so could you um could you show us a little bit of how the teleoperation node looks inside? I'm interested in that.
Mm, okay. Yeah. Okay. Okay, in this part,
Hmm.
um, we have the ROS2 node that will capture the key inputs, and then it will publish, will be the publishers. So the microcontrollers will be the subscribers. So when I send when I press a key, it will send the data
Hmm.
that the ROS2 node will capture,
Hmm.
and then the Raspberry Pi will send that data to the microcontrollers, and the microcontrollers will move the servo motors. And okay, as I mentioned before, in this case, the communication is with USB and Wi-Fi. And as we can see here in the diagram.
Hmm. And is this written in Python or what language?
This is with Arduino language.
Okay.
The ones that are running in the microcontrollers. Yeah, is Arduino.
Okay. Okay, so I have some more questions, but let me jump to some others that have been shared here. So
Yeah.
let me check here. We have a couple of questions.
Mhm.
Okay, so for example, Desire here is sending this question. Could you not do the work that MicroROS was handling with ROS, and why? What is the difference? What is the relevance of Docker in using SSH? Could you clarify a bit what you meant?
Oh, yeah, yeah. Sure. Okay. It's because on my Raspberry Pi,
Hmm.
I will use the Docker to register my robot to the construct platform. So in that case, I can control the robot from a project, even if I don't have with me the robot, which is in this case. So from the project, I will do an SSH to communicate with the robot.
Okay, okay. And about the choice of using MicroROS. So can you
Ah, yeah,
comment
yeah,
a little bit more about that?
yeah.
And yeah, what advantages it provides with respect
Mm.
to using ROS
Okay.
only, or
The mainly advantage is that it will have here I have the finger. I will have the nodes in the microcontrollers. So I mean, the microcontrollers would be allowed as a node, and in that case, I can communicate easily between the microcontrollers and the Raspberry Pi. So that's why I choose the to use microROS in the microcontrollers.
okay. We have another.
Mhm.
Okay, yeah, we have another question here. A couple more. A
Mhm.
new one came. So the second one by Desire is: may you please elaborate more on your choice of battery? Isn't
Ah, yeah,
5,200 a bit too small for the work that the robot might do in future, for example?
yeah. For the future, yeah, it is small, but for the moment, with the different servos that I have now and the different components such as the microcontrollers, I think it's okay to use this type of battery. But if I want to add like more powerful servo motors, of course I will need to change the battery to a more powerful one.
Okay, yeah, makes sense. And
Mhm.
let's go with this question by Lin Byte, Lin H Byte. He
Mhm.
or she is asking how many servos are connected to each MCU, microcontroller unit. Are you using some multiplexer or directly PWM from the microcontroller to the servos?
Yeah. In this case is directly, but yeah, there are many servos connected. Yeah, it is about mm, like 18 servos. Yeah, but of course, I will use in the future a multiplexer, so I can arrange better the using of several servos at the same time.
Okay, thanks a lot. And let me go with a couple of more questions that I have here written. So, for examples, are the fingers of the hands controllable? Because in your initial demo, they seemed like they were
Ah,
moving a bit loose. So,
yeah,
are those controllable, or is it planned
yeah.
to be controllable individually, or?
They are controllable,
Hmm.
but the problem is that sometimes the with the communication is not working properly. So that's why sometimes it disconnect and doesn't allow to control them. But this is one of the challenges that I face with this project, which is a like here. So that's why it seems that the fingers cannot be controlled. But well, mainly it is supposed to be controlled. But yeah, sometimes with the servos I have some issues.
Okay, so they are meant to be controllable, but
Mm.
it's
Yeah.
not super robust currently. Sometimes it
Sometimes it's not
works.
working properly. Yeah.
Okay, and can you control them individually, or how that
Yeah.
works?
Also individually.
So you can send signals to each of the fingers, right?
Yeah.
Okay, and yeah. So another question that I have, I think probably I'm going to be closing with this one, is so whenever you have, you were showing earlier that all those terminals that you had in the project running, that were starting different programs. So at the end, when you have everything started, in terms of ROS2, do we have some topics that we can access to directly control the robot, or how does that work?
The topics, for example, here we have 3 topics. This is the first one is the left key CMD. The other one is the right key CMD and the head key CMD. Each one of the left and right key CMD is to control each of the arms, and the other one is to control the head key CMD.
Okay.
So these ones are the topics.
Okay, these are the 3 topics that we would see, right? For the robot?
Yeah.
Okay, and what kind of messages do they accept?
Okay, is the... Oh, I don't have... Okay.
So you can, for example, do a ROS2 topic pub, let's say, simple ROS2 topic pub, or create a ROS2 publisher, create a message, publish it there, and control that. But
of course you can.
What kind of message it uses? It's like floats or
strings. No, the thing I have here. Yeah, it's strings because it will detect the different types of keys of the keyboard. So it will be a string.
Okay.
Because are the letters of the keyboard.
Okay, got it. All right, Alan. So let me. Let me see if we can see you again, because I'm trying here to. Where? Yeah. Okay. Yeah. So I am trying to. There we go. Now we can see you. Okay.
Okay.
Because
Perfect.
we were still seeing your screen. So.
Yeah. Stop share.
Yeah. Okay.
Okay.
All right, Angelo. So, thanks for your presentation. If you want to say some closing words, you can say them now.
Okay. So, thank you so much for all of you for attending my presentation, and I hope you really enjoy this project. And what else? Thank you so much.
All right. Thank you, Angelo. See you.
Okay. See you.
All right. So I think we have already here Alan. So let's see if we can receive him here and say hello to him.
Monica.
Hello, Alan. Okay,
Hello.
so we can see you.
Yes, I cannot see you. That's the bad sign, I think.
Okay, as long as you can hear me, we are good. We are good.
Okay,
To
great.
see me, you would have to open the live stream. But
Open the live
it's not
stream. Okay.
necessary. It's not necessary. Don't
Okay.
worry.
Yeah. Sure. Yeah. Sure. Okay. So the problem is, yeah. I don't know. It never happened before. I cannot, like, the code is compiling for ages, and I try to do it like multiple times, and I honestly don't know what.
Okay, we can have. So, were you planning to start with the demo, or first go with the presentation, or?
Yeah, I was. Yeah, with the present. First, I was going to start with the presentation, and then like simulation and real robot
Okay,
demo.
then
So
we can
we can
do.
start.
Yeah,
Yeah.
we can do that. Follow your idea if you want, and then afterwards we can have a look together. You can share your screen there in the project, and
Yeah.
we can see what's going on.
Okay. So now, because I'm not gonna lie, this is my first Zoom meeting, and I need to see how to.
Okay, it should be there should be like a bottom bar somewhere there, and
Yeah.
in one of the buttons it should say share.
And there's a camera. Portrait. Share screen. Yes.
Okay. We cannot hear you now, Alan. I cannot hear you. I don't know if you maybe muted something by mistake or. If you want, also you can try like leaving the meeting and rejoining or something like this, if you want. Oh, I see that you are typing. You are typing to me. Ah, okay. So there are some issues there with sharing the screen. Then let me meeting ID. So the ID, I guess it should be this one, or it's asking you to. Sure. All participants. Okay. So I think that Alan is going to be rejoining. So let me show myself here until then. Okay. So yeah, let's see if we can solve this issue with Alan and we can continue with the presentation. Okay, we have Alan coming back here.
Yes.
Okay,
Yes.
Alan. Yeah, we can hear you now. We can also see you.
Yeah, I know that. But unfortunately, on the using the browser Zoom, I cannot share my screen. I can do it using the desktop app on my Mac, but unfortunately, it always asks for some like access code for the meeting.
For some access code for the meeting.
Yeah, not like a hyperlink, but some code. And even if I click the link and I say that open with the Zoom app, it always opens up the browser and asks for like meeting ID or something like this.
Okay, that's weird.
Yeah.
Let me see if I can. Windows. No, I don't see anything from here. Okay, and if you right now you are in the web browser, right?
Yes. I am on the web browser, but when I click the link and I want to open it with the app, it opens up another tab in browser and tells me to input some.
Okay, I have one. Let's try with this, Alan.
Yeah.
Because
Yeah.
my colleague here sent me a code, which might be that one. I have just sent it to you.
Yes.
Let's see if this one works. Okay, I have you here now.
Yeah. Okay. But from my perspective, like nothing really changed. Okay. Now I can share my.
Okay, there we go. There we go.
Finally.
Yeah, we got it. We got it.
Okay, so you see my Discord, right?
Yeah,
so let's
we can see,
let's get rolling. The keynote is here.
Yeah, so things from the live streams. No problem.
Yeah. Okay. Can you see my presentation?
Yes, we can see it perfectly.
Great. Yeah. Sorry for the date, but as you know, this presentation has been postponed a few times, and I hope you don't mind the copyrights because this is like
not at all.
Yeah. Okay. So the presentation topic is autonomous shelf finding and delivery. Let's get started. So what do we want to achieve by doing what I wanted to achieve doing this project? So let's do some simple problem breakdown. I needed to set up the robot to be able to autonomously navigate in the warehouse, right? And the end result by doing this should be just we should be able to use the goal poles in the Ervis, right? So we can send some navigation coordinates to the robot, and the robot should go there, right? The second, actually, the main part of this project is implementing shelf mission logic. So the end result would be that somehow the robot would find a shelf in the warehouse and would drop off it wherever we want it to be drop off, right? Those like sub points to do is for example, we need to find the shelf, then we need to go under it, pick up and go to the drop off, and basically it's like leave the shelf and go back to the initial position. Also, we want to I need to create like a web interface, and the end result would be that there is some kind of interface that we can choose the drop-off position, or just check on the status of the mission, and do some very basic like modifications, right? And fourth thing that I needed to do is documentation in the form of this presentation that you are watching right now. How the system architecture looks like. This is like very basic, very like abstract general form, but we have this web user interface that I told you about, and through this, through ROS bridge that will connect to our ROS2 system, we can and through the web process manager. Web process manager is basically like a backend to our front end. The interface, and web process manager basically just launches the launch files responsible for example, shelf mission executor, but also for doing basic nav2 navigation, or using the joystick. But Shell's mission executor, his like main goal is to run and orchestrate like our custom behavior trees, or maybe not custom, because I actually used on two, not custom ones. And so how the robot will search first search for the shelf. It will go, as you can see on this picture on the left, it will go from waypoint to waypoint. Those waypoints are W1, W2, W3, right? So it will like go through this path to always have sight of the warehouse on the back of the robot, and the robot will like scan the LiDAR scans, but the scan is sliced only on the sides of the robot, and I did it for 3 reasons. First of all, to reduce the noise, right? Because I actually worked in one warehouse, so but most of warehouses looks basically the same as Amazon warehouse. So we have like shelves, and you don't need to look everywhere for the shelf. You just need to look on the sides, because you can, if you're able to customize the waypoints, you can always tell the robot to go wherever it's needed, right? Then I wanted to reduce at least a little bit the computation time, because if you need to iterate over a whole LiDAR scan, it can take some time and resources. Yeah, there was a third argument, but I forgot. But maybe later I will remember what was the third reason behind this. So yeah, how the robot finds the shelf. I will not go into like very specific detail. If you want, in the like Q&A section, I can totally do it. But basically, it's not magic. Basically, we just analyze the LiDAR scan, and we search for those. As you can see, the arrow here, we look for most like scans with the highest intensity values. And those are in RVs, for example, they have different color, because the intensity, the reflection from the scan is much higher. So we can easily find those, right? And if we find the clusters of higher intensity, if we find the clusters made of higher intensity laser scans, then we know that this object looks like a shelf, but it doesn't need to be shelf, but it looks like a shelf. So we need to look closer to it, right? Yeah. So we use basic math to change the the polar angles, the polar coordinates to Cartesian. We use some Pythagorean theorem, and we use some like atom function to, for example, find the norm of the shelf, because it was very important at one point of this project, where I could find the point, the exact point that's like in the middle and in front of the shelf. But then I realized I need to find the norm of the shelf, because otherwise this point was just too small and too much noise. And sometimes the robot was looking. He was on the point, but not looking exactly straight at the shelf, and this was the problem. How do we set up the autonomous navigation? Very simple, with nav2 toolbox. So like nav2 framework, not toolbox. So first we had to create a simulation warehouse map and real robot warehouse map using SLAM toolbox, and then we had to configure the planner and the controller and EMCL to help the robot localize itself on the map, right? Why do we use behavior trees in this project? Because mission is not linear, so there is almost impossible to write this kind of code as a object-oriented programming or as a like functional programming, because I would have to use like at least 20 layers of if statements, and it would be very unpractical and almost impossible to do. And doing this with the help of behavior trees is super natural thing to do, because there's a built-in recovery structure. So what happens if doing anything in one custom node that doesn't work? What to do next? Doing this in like normal standard functional programming would be basically a nightmare. We would have to use some like a state machine with like dozens of states, and yeah, that wouldn't be fun. And why this is very natural? Because when I was creating those like custom nodes for behavior trees, there were very many moments where there was some problem, and for every problem I had to create separate behavior trees, right? And sometimes those problems occurred in the middle of my, like, let's say, sequence of finding and delivery of the shelf. So doing this in like normal programming way would be a nightmare, because you would need to like put some logic inside the code, like somewhere in the middle, and yeah, in behavior trees you have all the nodes responsible for one, or maybe not one thing, but one logic, let's say, and it's very easy to build like from Lego some kind of behavior. That's why they're called behavior trees, I guess. And so yeah, the clear integration of different actions. So this is it. Now I will show you some. I sliced my behavior tree on some parts, so we can look at it. First, we have like init shelf mission, and this just creates the blackboard, creates the variables. But one node that I really wanted to like give your attention on is custom drive on heading, and this is exactly this refers to exactly what I was saying. This node, that basically what it does, when when the robot is patrolling here, patrol until find the candidate, but finding candidate was like too long to write it. Patrol until candidate finds the shelf, and then this node didn't exist in my simulation environment, because in simulation, when the robot found the shelf, simulation is very binary. So when it found the shelf, it was like 100% sure it's there, and the data didn't change because it's a simulation, right? So if he saw those like intensities, higher intensity values, they were still there. But in real and real robot environment, there was so much noise that when the robot found the shelf, how the robot finds the shelf, I will explain later. When the robot found the shelf in in split of the second, he would lose this shelf, right? So I had to implement this like custom drive on heading, and this node basically just makes the robot to drive on heading for some X amount of seconds or distance or whatever. So yeah, this is pretty much it. And in each shelf mission, we just create those variables like candidate left leg. So it's like candidate for left leg of the shelf, right leg of the shelf, where the pre-dock pose should be. What are our waypoint, like patrol waypoints is, so where the robot should go, etc., etc. In patrol until candidate, we can slice out our scan, so it only sees from 52 index to 305, for example, and it passes onto the next nodes, candidates, and where's the center of the shelf, where's the left leg, and etc. Then we do this custom drive on heading, so we go like 5 centimeters to get better look at the shelf, and then we validate the shelf. So here is basically the same that we do in patrol until candidate, but now we validate, because sometimes it might look like a shelf but not exactly be a shelf. So those like requirements for the shelf are just a little bit more like strict, And in part 2, we compute the pre-dock pose, so where the robot should go in front of the shelf, right? So we go 80 centimeters before the front of the shelf. In part 3, we refine shelf geometry, compute pre-dock pose again, and we adjust to pose local. And I wanted to bring our attention to those 2 nodes, because we do compute pre-dock pose again and adjust to pose local. And adjust to pose local, basically, this is the time where we don't use nav2 stack to move the robot, but in adjust to pose local, we like program controls the robot on its own. So the speed is much lower. Because we need maximum precision to be in front of the shelf before the docking, right? Refine shelf geometry, basically, again, we just refine the shelf geometry, so we do exactly the same as in patrol and validating. And adjust to pose local, exactly as I said, we take control of the robot, because we need absolute maximum precision before the final step, right? And yeah, part 4, dock to shelf, switch to carry mode, and custom backup. I want to bring your attention to custom backup. But first, let's see all 3 like parameters for the because those are like parameters for the behavior trees, right? Yeah, dock to shelf, nothing really interesting. We just if we have the exact position of the shelf, and we are set exactly right, then we just go under the shelf and we run the elevator up. I believe this is not a service, it's calling the topic. Then we switch to carry mode, so we make the robot much bigger. We expand the footprint of the robot, so it doesn't bump on the obstacles, right? Because nav2 stack needs to know that now robot is much bigger than it used to be. And custom backup. Why do we do custom backup? Because it could be that the shelf is in the middle, in the middle of other shelves, or very close to the wall, or somewhere where it's very like tight and narrow, So what I did, I created this custom BT node that first, before the docking, it checks the sides of the robot where there is more like free space for the robot to back up, and then this parameter is passed all the way to the custom backup, as you can see. So if there is a wall on the left, for example, in the refined shell geometry, the robot will pass this information further, and custom backup will go back with the shelf, turning into opposite direction. So it will not turn into the wall. And why is it custom? Because custom like backing up, because nav2 stack wouldn't allow us to move, basically, right? So we need to move the robot like semi-manually, and then we can pass the control over to nav2 stack, right? Okay. And part 5, I will go very quickly, but it's basically the same as part 2, I believe. We just do it in opposite direction. So we compute the pose for the drop off, and we place the shelf, and we switch to normal mode. So nothing to I won't say nothing interesting. No, it is interesting, but we like recently discussed all of this, so nothing nothing interesting to focus on right now. Next, this is basically how our web interface looks like. So first we need to put our ROS bridge address. That after we connect, we need to start the nav2 stack. If we don't do it, we cannot do basically anything. We do self-localization, so we make the robot to like reset the where the robot thinks it is. Do like a spin, sometimes 100 degrees, sometimes 360, and yeah, when the robot is self localized, we can do something with we can start our mission, basically, right? What are the constraints and possible solutions for this project? We have no real perception during backup, and this is like the biggest problem here. I let the robot to go back even though there is no perception back. And why I did it, I very hard tried to not to do it, but I had to do it because of something I call a ghost optical. Here, as you can see, nav2 stack thinks that there is some kind of obstacle outside of the robot footprint. This green is a robot footprint, right? And we know for sure that the only obstacle is here inside, right? But I don't know why. Probably because the laser lights maybe scatters a bit So he thinks that there is some obstacle right there. That's why sometimes nav to stack doesn't want to go further to go like forward. That's why I let the robot to go back, because for the robot this is the only possible way. Like nav2 will only be able to compute the path if we allow the robot to go back, right? And yeah, the second problem constraints is hard-coded mission parameters, and mostly I mean those parameters like waypoint paths and drop-off waypoints. And I also try to create some like dynamic parameters editor in interface. But then I quickly realized what I had to do is to create some like, template for the behavior trees for the behavior tree. And based on this template, I would have to dynamically create those like one-time versions of it. It's very similar to how templates work in C++ language, actually, where they dynamically create those like on the go, whatever it's needed, right? And it was way more into just interface web programming, and it has little to do with robotics. That's why I decided to leave the hard-coded parameters in the code. And yeah, of course, the possible solution for the lack of the backside leader would be 360 degrees leader and some like warning light and sound. And because this solution is absolutely the simplest. And yeah, if I know one thing, is we should always pursue those simplest solutions, because I tried very hard to somehow make the robot to dock to shelf, almost from the patrolling, right after the patrolling. But then I realized what actually works in this project is to make those like small increments. So first patrolling, then you go closer to the shelf, then you refine the shelf geometry during the validation state, then you do it again and again, because it's much simpler. And then fine-tuning the behavior trees parameters, or the scanner logic parameters, right? So yeah, this is how I would approach those constraints, right? Yeah, so this will be the end of this presentation. I hope I didn't talk for too long.
No, it was very, very, really interesting. Lots of
thank
very
you.
interesting details you were explaining. I was taking here notes for asking later.
Yeah, sure. Okay, I think you can see my screen, and yeah, I cannot for some reason.
Yeah, let's try to give it a try and see what happens.
Yeah.
So I assume that the heaviest probably is all the behavior trees, which are written in C++, right?
Yes. All the behavior trees are written in C++, but actually there is something must be wrong, I think, because compiling never took this long.
Okay, let's do do something. Let's do something.
Yeah.
Okay, I think I know what might be the reason of this. Let me check here.
Yeah, sure thing.
So in the meantime, exit the project, Alan.
Yeah.
So
Should I
you
cancel?
can stop and exit the project. And yeah. So let me check this. Yeah, that's it. Okay, so then let me do this. We are going to have to wait for
some kind of rebooting the system, I guess.
Yes. So the issue, just for you to know and for everyone to know, is that basically right now you were using a smaller computer than you usually do. Okay. Because
okay, so that might be the issue.
Yeah, our masterclass students, we always provide better computers than for regular users, let's say. But in your case, your license was expired, so I just reactivated it now. And then, but you had started your project before that, so you got a regular computer, let's say. Then what I am doing now is basically killing the computer you were using, so that whenever you launch again the project, it's going to start a bigger computer.
Okay, yeah, great. Because you're right. I started. I opened the project before I texted you about the.
I think
about
you
the
can go already. You can launch again the project, and it should already. I'm going to be able to see it here. Yes, now you have been assigned a bigger computer. Now the only thing is that maybe it takes a bit longer to start, depending on if there is a standby computer ready to be taken or not, and it needs to start from. I think we are going to be good. We are going to be lucky, and it's going to be more or less fast. Yeah. Yeah, this will take some seconds to finish initializing, but it should be fast.
Yeah. Okay. Yeah, we got this. Okay.
Okay, so first I see that you are going to show the simulation, right?
Yeah. I'm running the simulation. Sometimes, you know how the simulation works. Sometimes it needs to be killed, and then. But yeah, I think it should be good. Or maybe not.
Let me ask you, meanwhile, we are doing all this, because I saw during your presentation that you used the SLAM toolbox.
Yes.
Instead of cartographer, for example, for generating the map and all that.
Exactly. And if you want to ask me why,
I wanted to ask if you notice any interesting difference. It was better, worse, easier.
Okay. Antonio, I swear to God, there was some reason why I didn't use cartographer, because on every like checkpoint or anything, I used cartographer.
Yeah.
There was some reason, but it was so long ago that I don't remember. I think that it was something to do with with how it runs with. I don't know, but basically it's the same tool.
Yeah, very
but
similar. Very similar. Yeah.
Yeah, very similar. I think there was one checkpoint when we used the Slam toolbox, or maybe not. But yeah, basically it just generates the map. So, but I think there was some, but it was so long ago. I don't remember. But yeah, I think because Slam Toolbox is made by the same guys that run the nav2 toolbox. I think this was the reason. This is like one second cartography, something like
by Steve Szpetmański and
so probably that's why, because still I didn't know that back then, so probably this was the reason. I didn't know how old the version of ROS and nav2 stack on this environment is. That's why I had to, even those that's why I always say custom nodes, because I had to write even those nodes that already exist in the in this like framework. I had to rewrite because, for example, there is exactly the same node that just makes the robot backup. It's called backup, and there is a parameter that you just set the flag ignore collisions or something like this. And I'm like, yeah, perfect. This is exactly what I need. But unfortunately, this goes only for newer version of ROS. So everything I had to do like custom. So now we are running the West socket.
So let me just very quickly ask to the audience, because I saw a message here. I cannot hear Alberto well. Can you hear me well?
Yeah, I can hear you very well.
Okay. Okay, so if someone else also from YouTube can confirm, that would be great, so that I can be relaxed. And if there is some kind of noise, let me know, because I have a fan running here, so maybe I can turn it off or whatever. Anyways, yeah, so all yours, Alan.
Yeah, okay. I will try to first web. So our simulation is working. Now we should just visit the site where our interface should be hosted. I will make it look nice in a second, but at first I want to connect to it and see if everything is working. Okay, and now what we can do. Okay, so first let's focus on the website. As you can see, we cannot do much without starting the nav2 stack. First of all, we need to check the mode, if it's simulation or real robot. We leave the simulation, and what we can do is we can show the warehouse map, so we know where the drop-off waypoints actually are, right? So yeah, we start the nav2 stack, and in few seconds exactly, we should see the RVs with our robot. The robot doesn't know where it is right now because, yeah, let's make it harder. So we start the self-localization, and by doing this, we reset every parameters, and we make the robot to rotate and look around and see where it is, right? So yeah, that worked, because the robot is indeed in this place. Let's see if our joystick works. We can each side of the interface has its own logs, but we can hide all of them for now. Yeah. So as we can see, or maybe I will. Yeah, the robot is moving. The joystick is working, right? And now the screen is way too small. So now we can start our mission, right? Here we have some like basic information where the robot is, what's the angular and linear speed, basic stuff. So I will ask our audience, and Alberto, you can tell me where the robot should go. Should it go drop off the shelf on the drop off number 1 or number 2?
Okay, so whoever wants,
You can decide.
Yeah. Whoever wants 1, you can type 1. Whoever wants 2,
Yeah.
you can type 2 in the chat, and then the
Yeah,
one that has
let's make-
more votes will go for that one.
Yeah, we'll make this entertaining.
I'm going to vote for example, 1. There is a little bit of delay between us talking
Okay. So
and the
okay,
YouTube live, so maybe it's going to take some
Okay.
seconds for them to.
Yeah. Or we can just say it's 1.
Okay, we are starting to receive now.
Yeah.
For now, it's
Okay.
winning number 1. So
Okay.
let's go for 1. Yeah.
Yeah, let's go for 1. So we run our BT mission, and as what? Huh? What the heck it happened? Yeah, that looks like some
sourcing,
compilation
or some sourcing issue rather than compilation.
Yeah. But the thing is,
maybe you compiled and forgot to source or something like that.
I think I sourced because the sourcing problem would be somewhere here, right? Or maybe I was on the wrong package, not found. This is weird. I basically checked it on before the stream. Let me check on which Git branch am I. Yeah, sure. I think that might be this. Yeah, we're not on main. So okay, let's do it. Let's do it one more time. Sorry. Sorry for the.
No worries.
Sorry for this, because what I did, I checked the simulation, and then I for some reason I because I wanted to have like clean source, so I deleted all of this, recompiled, and this was this time where I couldn't like recompile till the till the end. So yeah.
So it's always interesting to see all these live. So
yeah, but basically this is what we do. This is programming live.
Yes. Yeah. And the good thing is being able to detect quickly. Okay, so this is what's happening.
Yeah. So we need to compile it again, but now with the bigger computer should be pretty fast. Is that okay? And here everything is that. Okay, nice. So maybe you have some questions right now, so we don't.
I have many. Yeah, I
Just-
can, for example,
yeah.
start by one, and let me also remember the audience that if they have any questions, please
Yeah.
share them there in the chat. So let me try to find one that can be. For example, just something
Yeah.
quick. So, do you have any way of visualizing the behavior trees flow live, like Router, for example?
Live, no. I have like one big, very not easy to look at visualized tree, but because there is so many, so many branches, it really needs a lot of like scrolling in and and looking at it. I never had. I never really thought about visualizing the tree because I didn't really know what would I do with it.
Yeah, so for example, there's a tool. The most common one is Groot. Is known as Groot, and
Groot, okay.
basically the value or the interesting thing that it provides is that you can see the how the different behaviors move from one another. If it's moving from one to another, if it's falling back because there's been an error, and all these transitions and all these, you can see live what's going on.
And what do you mean live? When the program is working?
Yes.
So
For example,
when the executor
when the patrolling behavior starts, you see it highlighted, and then you see
Okay.
when it transitions to another behavior, or if which path it takes, depending on if it's a success or if there is some kind of error, then it's going to fall back to another behavior, and you can see all these transitions live and all this.
Okay, that's actually that's great. And so after the presentation, you can you can send me the name of this because now I will probably forget. Come on, guacamole. Oh, yeah, or no, this is old simulation or the new one?
Yeah, there is. So probably what you should do is to stop and kill the process, the gazebo process manually, because you can see there are two there open.
Oh yeah.
So
yeah.
that indicates that there is one ghost simulation there. So probably there's going to be some problems there. So what I would do is just Control C here, and then do a PS. Yeah, you can confirm there, for example, from the guacamole, or just do a PSF. Yeah, just kill that GZ client. That's the ghost one.
Okay. Let's source everything just to be sure.
Yeah, gazebo sometimes does these things. Yeah, now it looks good.
Yeah. Yeah. It should be the same.
Yes, the it should be the same, the address. Yeah.
It should be the same. Okay. So now you can hide the map. Yeah, we see the robot. We start did we do it? Okay, the simulation works. It's not frozen.
Okay. Yeah, this looks correct so far. So
Yeah.
we were not seeing the
But
map
let's
earlier, so
yeah.
maybe it was that. I would try again.
We
Just try again.
Okay,
There
now
we go.
it's working. Okay. Okay, and now a bit of trivia. The reason why the robot spins only 180 degrees, and I demonstrate that the joystick is indeed working, is because in simulation this warehouse is doesn't have a lot of like distinction points, and sometimes, very rarely, but sometimes the robot thinks he's on the cross on the cross from this point, right? And when it's moves around, then he like understands, okay, I'm not actually there, but I didn't want to like waste your time with it. So yeah, let's do it again and see if now it will work, because exit on finish, this is my parameter, and we trigger the mission. So the robot is going, he's patrolling, so he's going to the first waypoint, which is somewhere in the middle, right? I will, if you want, I can move around in the simulation, but sometimes it can freeze. So I will try to do it one, so we see everything. Yeah, okay. So we see everything, and we don't make it like freeze, right? So custom drive on heading. Yeah, he's computing the pre-doc pose. Yeah, for example, right now he doesn't see the. This is actually good that it happened, because NAV2, as you can see, the front of the robot is not exactly like facing the shelf, so it cannot confirm that this is actually a shelf. So he will come back to the to patrolling again, right? And so that's actually good that it happened, because you can see if how this this behavior works, what are the like recovery behaviors and etc. So now we are computing the pre-doc pose. In simulation, sometimes it takes some time. Okay, yeah. Adjust to pose local. So now the robot will go very, very slowly for the like final pre-dock pose. And yeah, now we start docking. And during the docking, the robot, of course, is corrugating. Like it corrects its position. Now this is custom baking. As you can see, the robot is doing like an arch, because there's a wall on the left side of the robot, right? And you can see on the RV's map that the inflation radius around the obstacles is much bigger, because now we carry the shelf, right? We can confirm that the first drop off is in the middle of first and second shelf. Yeah. So the robot is putting the shelf. And what's funny in this simulation, I will not run this simulation again, but if you run this simulation and the first thing you do is manually send the elevator up, the shelf will magically appear on the robot immediately. That's the funny there's a funny bug. And now the robot is coming back to the initial position, backing going in like backing up, not going in forward, unfortunately. So yeah, this is for the and because as you can see, those reflective parts of the shelf are now from the other side. We cannot redo in the simulation. We cannot do the number 2 drop off right now because the robot wouldn't find the shelf, because the moment we take the shelf up, it somehow changes the orientation. So what about going to the real robot part?
Let's go for it.
Yeah,
sure.
Yeah, let's go for it. Connect to my favorite robot. Book your slot. No. Oh yeah, connect. Okay. Both cameras are working, which is very nice, because I will tell it right now, so I don't excuse myself if in case something breaks. Sometimes when there was some like network issues, I think I'm not sure. Sometimes this code didn't work because there was some high latency, and the TF messages were not like in sync. But now I see the cameras are working. The quality is good. I can see the latency. Ooh, it's 250. Okay. Okay. Yeah. Let's see. Ross Bridge. Okay. So now we only need this and our web app. Let's see if it works. So now we change the mode to real robot. And we start the nav2 stack, and let's see if it indeed works. Okay, we have our map. Now we will start self-localization. Yeah, okay, it works. Great. At least that. So with the real warehouse, no problem. We can do whole 360. There's a lot of like distinct points. So yeah, let's do it again. Let's ask our audience where do we want to go. As you can see, I will try to do it on maybe control. No, how to make it bigger. Okay, yeah, that's absolute maximum. So the number 5, 1, 2, 3, 4, and 5. Actually, 4 is next to the charger. 5 is where the shelf is on like by default, and 1, 2, 3 is just I'm not very creative.
Okay, so I'm going to say, let
Yeah.
me say 4, for example, myself.
4.
I'm going to
4.
vote 4. Let's see if we can get some votes here.
Yeah,
Which one
sure.
wins? The shelf is properly placed?
No, because those like it shouldn't be orange, right?
Okay, so we should have the white ones?
Yeah, but I can do it using the.
I think we can. Let me ask. I think Roberto is around here, so let me ask to
Yeah,
turn it around.
it depends because it's Friday. I know that you guys want to have like a weekend. I can do it and showcase that my joystick and everything is working. But if you can ask,
Yeah, it's going to be faster. It's going to be faster. And
okay, yeah. This is what I thought.
yeah.
Sure thing.
Yeah. So yeah, I think that we have recently installed these new panels here also. So we have reflective panels in both sides of the robot, in the rear robot. Okay.
On the shelf, right?
Yes, on the shelf.
Yeah. So it's reflective, but the intensity is different than, or is it the same?
It might be different. So that's why I prefer to do it with the classical ones.
Mm-hmm.
That are the ones
Okay,
that
yeah.
you've probably used for all your
Yeah.
tests. So yeah.
Yeah, I thought those like oranges are just to this is just indication that the robot is orientated in the wrong way. So we know, oh no, it's orange. So we should like
I think they provide
turn.
also intensity values. I think, but yeah. So it's better just to try like this because
Yeah. Alberto, do you know which? Yeah.
So yeah, I would say let's go with 4 because.
Yeah, this is my favorite waypoint. Okay. So we trigger the mission. And yeah, here we have only 5 waypoints. In those like critical, I would say, critical places. So yeah, the robot is moving, and now let's hope for the best. Yeah, compute pre-doc. Now we did refine the shelf geometry. We adjust to pose local. We go under the shelf.
Yeah. It can be seen that it's elevating.
Yeah, and it's moving. As like previously, he detected the wall on the left side, so he's doing the arch. Oh, this is brave. This is very brave from him that he goes. I thought he will go. Robot, why are you doing this?
I think it's
eating
some of those cones.
Yeah, he's eating the cones basically. Yeah, I don't know why he just thought that's enough space for him to go, not to use the back movement. So I will. Jesus.
You are celebrating it now, right?
Yeah, like what? Yeah, now I'm. Why? Why? Okay, I don't really understand this.
Yeah. So now what we are seeing is like the front of the robot from here. So
Okay. So
you
I
can see
was
the red. Yeah.
yeah. Okay. Let's try again. Can you ask Alberto? Can you ask Roberto to put the cones on the
Okay. Yes.
on the place because I don't want
Sure.
this like task to be easier with the cones somewhere.
Yeah.
Jeez.
There we have it. Yeah. This should be.
So
This should be good.
yeah. But now I can showcase that the buttons are working. So elevator down, and we can.
Maybe we can even try, if you want, is to start the mission not from the
From
initial
here.
position, but or from just the middle of the.
Oh yeah.
Between the starting point and its current point, like, so we don't have to go all back.
Yeah, because the first waypoint should be somewhere here. Yeah, so we run the mission. Yeah, that's. So basically, what failed was I had to misconfigure the nav2 somehow because going from waypoint to waypoint or from with the shelf, yeah, but I don't think because right now. Yeah, the problem is right now we have old footprint.
I understand.
Yeah, but he can. Okay, I'm very proud of this robot because he smashed the shelf a bit, but with the wrong footprint. Yeah. It's as we can see, it's very. Is very bad positioned. So what we should do, we should restart the whole system because this is something I didn't do because it was also very like difficult and not much to do with the robotic itself. I tried to create the change footprint button because I had during testing I had some problems with this. And I wanted to have like quick way to change the carry mode from carrying the shelf to carrying nothing. But the thing is, I would need to hard code basically everything into the backend, and I really didn't want to do it. And what I will do, I will stop the mission when he leaves the. Because he more probably will smash it.
It's been
Yeah.
fine.
Okay.
Yeah. So
It's okay-ish. So we can choose another drop off, and now it's even better because as we can see, the shelf is not very like straight positions. So it will be a bit more difficult for the robot to do it again. And now he will change the. And now he will change he'll change the footprint after leaving the shelf, so we can do it again. Alberto, you can check. You can choose the waypoint now, so we go faster.
okay, so is it going to be able to pick it up from there? It should.
Yeah, it should be.
Okay,
It should
then
be.
let's go for 2, for example.
Let's go for 2. Yeah. And we trigger the mission.
Roberto is appearing there. You don't have to do anything, Roberto.
He makes it even more difficult.
He's trying to put it there. Okay.
Okay, can be very very helpful, Roberto, indeed. We compute the pre-doc pose.
Okay, so what would have happened if Roberto didn't move it? I suppose is that it would have continued patrolling a little bit more, right?
Yeah. He'll go somewhere near the
charger.
The charger. Yeah. And then to the initial point, right? And but what would happen if Roberto take the shelf with him?
Mm-hmm.
What would happen is the robot would do 2 circles and go back to edit position and actually finish the mission with success, because like he just didn't find the shelf, but the mission like ended with success because he did like 2 circles around the path, right? And there was no errors, there was nothing that interrupted the whole process prematurely, right? Okay, so yeah, now no cones ahead of us, so yeah, this one is it. That's why I like the number 4 the most, because the robot needs to carry the shelf for the longest distance, right? And yeah, the robot changed the footprint. I wanted to do like this, so we see all of this.
There we go. Okay, Alan, so I think we can leave the real robot demo here. I think we've been able to see it do many different things.
Yeah, actually, I'm really proud of the robot that it smashed 2 cones, but still was able to drop off the shelf and back without like carrying it through the whole warehouse. Yeah, because this happens during this had happened during the creating of this project. So yeah.
Yeah, so it's been very interesting seeing all these different actions, tests, both in simulation and real robot. And I must say that something that it's very good from your project, okay, it's that that you can switch seamlessly between the real robot and simulation mode. That's very convenient, right? Just by changing the button.
Yeah.
So that is super cool and super good design for your application. All right. So very well done there. And it has allowed us to switch between the simulation mode and the real robot very easily and do different tests and so on. So yeah, well done, Alan.
Yeah, actually creating this interface, it was not only like required by this final project, but you have no idea how much it helped me like during debugging, because right now I had only like 1 button to start all the nav2 stack and everything, or to lift the shelf manually with those buttons. Normally I would have to like copy this topic calling and or whatever.
Yeah.
So yeah, this was very helpful even in this stage of still like developing this thing.
Yeah, sure. And this is towards where robotics is going to go for sure, because everyone is going to be using robots in the future, but not everyone is going to have to know what a topic is, what a service is, what a behavior tree is. They don't
need this.
They don't care about that. They care about the robot starting things and the robot doing what it is supposed to do, right?
Yeah. At the end, we are not doing this for us. We are doing this for other people. So it makes sense.
All right, Alan. So thanks a lot for your presentation. Very interesting, very informative. I hope that everyone has enjoyed it. So let's try to close with a couple of quick questions so that we don't go too late in time. Then let me go over a couple of questions of my own, and then I will pick a couple from YouTube. So, for example, there was something I was paying attention there to all your explanations, and there was a specific box there that a behavior that catched my attention, which was validate shelf candidate.
Validate shelf candidate. Basically, it does exactly the same thing as when the robot is patrolling during the patrol until candidate custom node. It looks for some clusters of the intensity values. So first, it needs to create 2 clusters. It needs to be 2. Like 1 is too little, 3 is too less, and there are a lot of like parameters. So, for example, if the 2 points that are right next to each other in this like array of points, and there are too far away from it, the threshold is like exceeded. We can no longer consider this as part of the cluster. But I had to set this parameter. So, for example, it had to be like 3 millimeters or 4 millimeters or something like this. So, validate shelf candidate does exactly all the same things as looking for the shelf during the patrol until candidate, but all those parameters are just a bit more strict. So we don't. For example, with intensity. Because in simulation intensity is just 5,500, but in real robot is different. So we have a threshold that says, okay, everything above like 3,000 during patrol until candidate, and then during the validate shelf candidate, it's no longer 5,000, 3,400, but 4,000. So we need to be sure that this actually is a shelf. And since we are a bit closer to the shelf, because we after finding it during the patrol until candidate, we do this custom 10 centimeters going forward with the robot, so we have a better look on the shelf. We can expect those intensity value to be higher, and those clusters to be more like strict, and yeah. So this is what it does. It checks all of those like parameters. So for example, we expect the shelf leg spacing to be 60 centimeters, but I do some like tolerance, and during patrol until candidate, the tolerance is, I believe, 12 centimeters. So if we find something shelf looking alike that's like 45 centimeters during patrol until candidate, that goes. But during validating the shelf, it will not go. This node will dismiss this, reject this this candidate, right? So basically, all those same parameters, but more strict.
Yeah, very, very interesting and very smart to do this kind of redundancy to
yeah, I learned all of this based on my mistakes. So yeah.
That's the best way to learn, by the way.
Yeah, sure.
Okay, so I had another question, and I have seen another question here just posted right now in the chat, which is kind of related to mine. So I'm going to go with both of them. Let me start with the one from the YouTube viewer. And Lynn Byte is asking, how many nodes did you create and how do you group them into different packages? This is interesting in terms of designing your solution.
Yeah.
And then
I'm
going to go afterwards with my question, which is somehow related. But yeah, first one, this one.
Okay, so I will start with the second part of this. I don't group them at all, basically, because I never had the need to group them. And how many I created, I don't know, but let's check it right now because I have. Let's do it live. All those nodes. So if we just was a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30 nodes. We don't count the dummy mission nodes because this is like dummy mission nodes. All those nodes, basically, this might be interesting. All those nodes, once they were inside the dummy mission nodes, and all those nodes, basically, those nodes were passing the success. So first I created the skeleton with dummy nodes, and then I did implementation. And when I implemented one node, I refactored the code, so I took it away from the dummy mission nodes, for example, to like place shelf, and this node was replaced. So we had 13 minus dummy, so this is 12. But in switch nav mode, here I have actually 2 nodes because I have switch mode base, so like not real, default robot settings, and I have another node in this file as well. So because those nodes basically they do the same thing. Yeah, switch to carry mode, switch to normal mode. So for me it was very natural to put them in one file. So 13 nodes, and I just suppose custom backup and custom drive on heading. If you are using this person that asked the question, if you are using the newer version of ROS, you don't need to implement those. Those are pre-made. They come with the BT framework, let's say. So 13 nodes.
Okay, and then my question, which was related to this, is because of all these nodes with others also that you didn't create but you have to use. So did you have to at any point consider threading issues in your system? Like, for example, having to deal with too many callbacks running in parallel. Did you find or did you encounter any issues related to this?
I did not, and I don't know why, but I have a good guess why it didn't happen, because all those nodes, I very much wanted to make a node that does only one thing and one thing only. So that's why one specific node, they don't, first of all, they don't like work in parallel, and the most in patrol until candidate, we use the most sources of knowledge, let's say, because we are using the odometry and we are using the scan, but it's very like primitive. So I had no problems with threading. There was no problem with that, because those nodes are actually, they are for each node is for one specific task, and probably that's why, but I don't know exactly.
Yeah. So it makes a lot of sense. So yeah. And then let's close. Last question from Desire, who is also your tutor, has been your tutor on the masterclass. So let me
the greatest tutor.
Yeah. So let me go with one also that. So for example, please explain in a bit more detail why the laser scan processing is sliced.
Okay, yeah. Thank you, Desire, for not giving me a curveball. It's sliced first of all to reduce the noise, because I like the way I create the waypoints, the not the drop-off waypoints, but the patrolling waypoints is. I analyze how the warehouse looks like, and I always want the robot to be like from the side, from the shelf, right? So if I can do it like custom, if I can like modify it, I can make the robot to be always on the side, right? Because I don't want the robot to so there will be always the exact same distance from the robot, from the side of the robot to the possible shelf location, right? And it wouldn't be the case if if I let the robot to search for the shelf in front of, because in front of the robot would be moving, so it would see the shelf somewhere there, but all those values, intensity values and everything, it would change because the robot would approach it, right? And if it's on the side of the robot and I can control where the robot goes, and I know more and less where the shelf could be, then I can make the robot to be always in the best possible distance for me. And so we are reducing the noise because we are not looking everywhere, and we are reducing the noise in the way that he will always look from this one perspective, and the shelf should always more or less be in the certain distance. It doesn't mean that the robot wouldn't be able to see the shelf if it's like further away, but by this like, I don't want to say smart, because then I would say the good things about myself, but doing this smart thing, it makes this job easier for you, because the shelf will always be somewhere like 80 centimeters from the shelf, and it also just very slightly speeds up the computation time, because we are only checking those like here, from this index to this index, right? And we are ignoring the rest, so we can take another scan and do it again. And I have the third. Okay, so yeah, those are the three reasons: reduce noise. I know all the three. Reduce the noise, reduce just slightly computation time, and to make this job a bit easier by always being like on like 60 or 80 centimeters from the shelf. So those are those three reasons.
All right.
Thank you, Desire, for this question.
Yeah, and it's I can say it. It's a smart solution. So yeah.
Thank you, Alberto.
All right, Alan. So yeah, thanks a lot for your presentation. Really interesting. I hope that the audience has also enjoyed it a lot. And yeah, so if you want to say some final words.
Yeah, of course. I would like to thank Desire and you and the whole the Construct team, because yeah, this was some fun ride. I remember saying to Desire at the very start of this this journey that this is on the very much edge of what I am, or what I was capable of. And yeah, and I did it, and I'm very proud of myself, and very proud of you for doing the best way to teach robotics to other students, because it's very fun. And
Yeah, you have to be brave. So
Yeah.
Masterclass is
Yeah.
tough. It's for
And-
tough guys.
Yeah.
Not all the students that enroll finish the Masterclass. Indeed, and it's a little number, okay, because it's a
And-
tough program. So yeah, you can be proud of yourself.
Yeah, and if I can say one more thing, I remember there was some checkpoint during the masterclass where the behavior trees were like presented, right? And I did not understand a thing. I thank to God that the checkpoint was absolutely unrelated to the behavior trees. There was some like how to do custom behavior node and everything, and I didn't understand a thing. But it's very fun to learn it. It's very good for beginners because it makes you it forces you to program as beginner programmers should program. So always focus on one thing only. Create a function that does one thing, and do this. In project-oriented programming, there is this rule that modularity.
Mm-hmm.
So it teaches you modularity, and So if some students are watching this, don't give up on behavior trees. I know it's very intimidating at the start, but it's so much fun, and it's great for beginners because it sets your mind how you should approach problems. And
So there you have it.
yeah. So now a weekend for you guys. I
Yeah.
let you watch the Spain Belgium.
Yeah. I have been left
Yeah,
here
yeah.
all alone in the office already. I'm the last man standing. So yeah. All right. So thanks a lot one more time, Alan. We will be in contact, and
Yeah.
see you around. And for the audience, so thanks also for staying here. And for sharing your questions, for sharing your comments. Many people saying here, thank you to Alan, also from YouTube.
Thank you very much.
So
Thank you very much.
Then let's leave it here. And to all of you, we will see you with more students in coming presentation ceremonies. So stay tuned. And as I always say, keep pushing your robotics learning. Bye-bye.
Yes. Ciao.